in this example, we will be determining the charge to mass ratio using some Physics 1. Okay, a little bit of Physics 1 coming back, and using the idea that the force that a particle feels is related to the electric field that it is sitting in. Okay, so in this example, when released from rest in a uniform electric field, a certain charged particle travels 2 centimeters in the direction of the field, and it does that in 2.88 times 10 to the minus 7 seconds. The magnitude of that field is given right here. Okay, we can ignore any other forces. So the question is, what's the charge to mass ratio? So, well, let's start off with what we have just talked about in this lecture, right? And that's the relationship between the force and the electric field. So what we know, oh, that's not a very good, it's not a very good coloring tool or writing tool. Here we go. So what we know right now is that the force is equal to the charge that's feeling the field times the electric field that it's sitting in. Okay, so that's the force that a particle experiences when it's in an electric field. And so what do we know about this particular problem? Well, we're told the magnitude of the electric field, which is 1 times 10 to the 4 newtons per coulomb. And we're told that the distance the particle travels is 2 centimeters. So we could just say distance is, I'm going to go ahead and write that immediately in SI units, 0.02 meters. And that the time it takes to move that over that distance is 2.88 times 10 to the minus 7 seconds. So these are all of our givens. We're asked to find the charge to mass ratio. Okay, so problem solving technique here is like, okay, well, I know that we're going to be using information that was just taught to us, right? But we weren't giving any information about how mass is related to the force that a particle feels in an electric field. So how is mass related? So we need to bring in some Physics 1 ideas, early Physics 1, namely the fact that force, any force, right, is equal to the mass of the object moving and the acceleration of that object, right? F equals ma, that was, early Newton's laws, right? So F equals ma, plastered all over t-shirts, right? This is true for any kind of force, right? Not just forces of push and pull or frictional forces or gravitational forces, but it's also true for electromagnetic forces. So this particle that is feeling a force in an electric field, well, guess what? That force is also equal to F equals ma, right? Or equal to ma. So we're solving for the charge to mass ratio. So here's our mass, here's our charge. These two forces are equal to each other. Okay, so basically we have QE equals ma, where a is the acceleration of that particle. Are we given the acceleration of the particle? We're given this. We're looking for this, right? We're looking for this. Well, what we're really looking for, let's go ahead and rearrange it. We're looking for Q over M, which puts the right-hand side as A over E, right? So we are given this guy, what is the acceleration? So, well, we're told, I think maybe enough information to get acceleration. Remember that acceleration is the rate of change of the velocity as a function of time, right? So dv dt or delta v, actually no d, let's do this. It's delta v delta t, right? So what is our delta v? So our velocity here, right? Our delta v is, well, we know the initial, so it's V final minus V initial, and the time is delta t given to us. This guy is 0, right? Because it released from rest. So our initial velocity is 0. We still don't know our final velocity. So we're going to need to bring in a kinematic equation to figure out what the velocity is. Okay, so a little more physics 1 coming at you. Let's talk about what is the acceleration? Well, we're going to need to bring in some physics 1 here. Another aspect of physics 1, which you may recall, kinematics. Okay, and we're going to use the kinematic equation to find the acceleration. And so there were 3 kinematic equations that we used, and I'm going to just go ahead and tell you which one we will be using. V naught t. See if this looks familiar to you. Does that one look familiar to you? Right, so the reason why we're using this one is because we have all the information to solve for acceleration here. We know this is the distance traveled, right? Which is 2 centimeters. We know this is the initial velocity. It was released from rest, so that's equal to 0. And we know the time. Well, yeah, we know the time. The time was given to us. 2.88 times 10 to the 7 seconds. So this one makes the most sense. The other kinematic equations had unknowns like velocity that we don't know. And basically the other 2 have velocity in it, and we don't know the final velocity. We weren't told that. So we want to stick with the kinematic equation where we have all the knowns and only one unknown. So we're going to solve for A now. So let me go ahead and plug in my value. So I have 0.02 meters equals 0 plus 1/2 A, and then T, we'll plug in what T is. Okay. And then now A is going to equal 2 times 0.02 meters divided by 2.88 times 10 to the minus 7 seconds. All right, we plug that into our calculator here. And we get about 4.82 times 10 to the 11, and then the units of acceleration are meters per second squared. So that's a pretty significant acceleration. So now we can plug that into our equation, Q over M, right? That's what we're solving for, the charge to mass ratio. The acceleration, 4.82. Divided by the electric field. Okay, let's do another calculator operation. And that just basically reduces our decimal 11 minus 4, which turns that into 7. So what about the units? Right, we could do, we would basically, in order to figure out the units, we would break newtons into kilogram meters per second squared. Okay, and we would do all of our eliminations, and we would end up with coulombs per kilogram. So there's our charge to mass ratio. And so what happened here? Let's review. So basically, we had to do a little bit of problem solving. Basically, if we wrote down everything we knew and we wrote down the equation that we knew we had to use because we were just taught it, we were left with, okay, how is mass going to get incorporated into this? And this is where Physics 1 came in, the fact that force is equal to mass times acceleration. So any object that is accelerating, whether it's accelerating because it's in an electric field, is it accelerating because it's in a gravitational field, is it accelerating because we're pushing it, they all obey F equals ma. And so we would see a connection here, right, to set ma equal to qe, and that gives us a very simple relationship with the charge to mass ratio. And what we were left with is, okay, well, we figured out how m is incorporated. How was A incorporated? Well, to find A using information about distance and time, right? That's going to lead you, or releasing from rest, okay? That's going to give you clues into using kinematic equations, okay? So there's not a whole lot of problems that we'll be doing that bring in Physics 1 topics. It's just kind of when we start off, we like to bring those topics in because it's like, hey, don't forget, you spent the whole semester learning this. We're going to bring it back up again. But as we get deeper into Physics 2, there'll be less and less times where you have to refer back to Physics 1. And if you do have to refer back to Physics 1, we're going to go through the example together, and I will show you how Physics 1 comes back into it, okay? So that's example 16.5.